The hypergeometric distribution. While this distribution is not explicitly on the syllabus, and I think it's unlikely you'll come across it, it does say that we should look at examples of non-uniform discrete distributions. So we're going to have a brief look at the hypergeometric distribution, which is an example of this type of distribution. So what we have here is a box that contains a lot of red and a lot of yellow disks. The box contains two types of object. Let us define taking a yellow disk to be a success and taking a red disk to be a failure. We've come across this idea before. There's two possible outcomes. One of the outcomes we call success and the other outcome we say is a failure. The box contains the population of objects, in this case of size 30, and from this population we draw a sample. The random variable x is the number of successes in the sample. So if we decided to draw 10 disks, and we got 8 yellow and 2 red, we would say that x is equal to 8 because there were 8 successes. In the case shown above, the population contains 9 successes and hence 21 failures, making the total of 30 in the box. Suppose we take a sample of size 5. X can clearly take the values 0, 1, 2, 3, 4 and 5. In other words, we could get no yellows in the sample, 1 yellow, 2 yellows, 3 yellows, 4 yellows and 5 yellows. And we could, of course, work out the probability for each case. But suppose we took a sample of size 12. We only have the 9 yellows. So x could only take the values from 0 to 9. It cannot take the values 10, 11 and 12 as there are only 9 successes, i.e. yellow disks, in the box. We could look at this as x being able to take the values 0 through to 12 with the probability of x being 10 or 11 or 12 all being 0. However, this is really not what we do in practice. So in general, we only look at the case where the sample is less than or equal to the number of successes. We don't consider those cases where we take a greater sample than the number of successes that are possible. In general, we say that the population, that would be the number of disks in the box, is of size capital N. There are k successes in the population, so there would be k of the yellow disks. And hence, n minus k, big N minus k, failures. So if you think about it, the box has n in it. If there's k successes, there must be n minus k failures. We take a sample of size small n. There are kcx, or kx is another way of writing that notation, ways of choosing x successes from the k successes that are in the box. Think about this. Our sample contains x successes chosen from the k successes in the population. So if we relate it back to the yellow and red disks we had before, we know that there were 9 yellow disks. If we were to get 4 successes, there would be 9 choose 4 ways of getting those successes. Also, because we're moving on to this, for choosing the reds, let's say our sample was of size 6, there would be 21 choose 2 ways of getting 2 of those, and then we would have 4 successes and 2 failures. So there are n minus k, because that's the number of failures, c n minus x, or n minus k, n minus x. Ways of choosing n minus x failures. Think about it from the sample here. If we get x successes, we must have n minus x failures. So there are n minus k, c, n minus x ways of choosing the n minus x failures from the n minus k failures that are in the box. Think about this. Our sample size is n, so if we have x successes, we must have n minus x failures. These will be chosen from the n minus k failures. So that's this choice just here. And in the paragraph before, we were talking about this choice. Our sample will contain x successes and n minus x failures. So the number of ways we could choose such a sample is kx, or if you like, kcx, times n minus k, cn minus x. Perhaps a diagram might explain this. So let's say we've got a box, and let's just say it's split like that. And we know in total in the box we have n things. If we have k things that are successes, then we would have n minus k things that are failures. When we choose our sample of size n, if we get x successes, then we must have chosen n minus x failures. And we can see from the left-hand side of the diagram that that is kcx, and from the right-hand side of the diagram that that is n minus k, c, n minus x. Overall, the number of ways of choosing a sample of size n from the population of size big N is nn, or ncn. Hence, the probability that x is x is the number of ways we chose in our particular sample, which we discussed earlier, divided by the total number of ways. As discussed earlier, the number of successes has to be less than or equal to the sample size, and of course, x has to be less than or equal to k because there are a maximum of k successes.